Hi everyone, we're going to continue with Chapter 2 and finish Chapter 2. In this part of the lecture we talk a little bit about some special qualities of water. Water is an important substance. It's going to be pretty much a majority of what you and I are made out of, so we should talk a little bit about water. We also transitioned to talk a little bit about this concept known as pH, what we mean by that is acids and bases and what types of things those are. And then we will conclude talking a little bit of what are known as functional groups. So to start, water has a couple of interesting properties to it that make it so valuable. The first is that it's polar. Okay, remember when you're looking at a molecule, it's got two atoms of hydrogen attached to an atom of oxygen like this. Oxygen wants to pull those electrons in towards itself, so it makes it slightly negative, slightly positive on the hydrogens. And these things here, the partial charges, these are called poles, so we call it polar. Okay? And stuff that's polar is hydrophilic. So remember, because water is polar, any other substance that's polar is water loving. So water likes to be with things that are like itself, and because it's polar, it likes to be things that are like itself in the fashion that they are polar. Okay. Also, water, like many other substances, has three stages to it, three forms. It can be at one time a liquid. It can be at one time a gas and a solid. So an example is that let's say you have a beaker of water and there's a whole bunch of water molecules hanging out, loving life. And let's say you heat, let's back up for a minute. Let's say there's a little bit of these things called hydrogen bonds bonding between these water molecules. Again, remember that the slightly positive charge on a hydrogen of one water molecule is slightly attracted to the slightly negative charge on the oxygen atom of a different water molecule. Okay, so let's say at any rate we have all these hydrogen bonds and they're kind of attractions between water molecules. Okay, well, when you heat all of this water up, you can actually break apart these bonds, and then suddenly each of these little water molecules are free to leave, and then they become, suspended in the air, and that would be the gas form. On the flip side of that, you can actually cool this stuff down, and it actually makes these hydrogen bonds more solid. I mean, they're still relatively weak. They're not going to be as strong as an ionic or a covalent bond, but it does make them a little bit more rigid, trapping some air bubbles in here. And this is known as ice, would be the solid form. And ice, again, the reason that it floats is because of these small little air bubbles that get trapped between the water molecules. So it all has to do with hydrogen bonds in this particular example. And here we have some nice floating ice. By the way, if ice didn't float, and let's say the solid form of water was more dense than the liquid, which is the case for almost every other thing. So water is the exception because the solid is actually less dense than the liquid. Most of the time it's more dense when you have a solid of something. But in either case, if it wasn't the case that water was less dense, meaning that ice, the solid form, would float, what that would mean for you and I is that lakes would freeze completely during the winter. So if this was a lake, ice would freeze from the bottom up. Also, the polar ice caps on the North Pole and in the large amount of ice in Antarctica on the South Pole, all of that stuff, if that sank to the bottom, it would raise the ocean such that all of land pretty much would be covered, and then we'd have like water world. I don't know if you've ever seen that movie in the 80s with Charlton Heston. Well, anyway, I think it was Charlton Heston. At any rate, that's a little bit about the gas, liquid, and solid of water. Water is also known as what's called the universal solvent, meaning it can form solutions. Okay, and a solution is a word to describe something that has two parts to it. There's going to be a solvent, and there's going to be a solute. So the solvent is like, you can think of it as this is kind of the liquid part of the solution, and then the solute is the stuff that's put in it. Okay, so this is the stuff that's dissolved into the liquid. So an example of these, oftentimes the solvent is water, and then the solute would be something like salt, table salt. You put some salt in water, it dissolves. The salt is the solute. The thing that's dissolving it is the liquid part, which is the solvent. Okay, so you want to know the difference between these two terms, solute and solvent, and more often than not, the solvent is generally water. There aren't many other liquids out there that we dissolve much stuff into. One of the things that can happen when you are dissolving something in a solvent such as water is this word dissociation. And we've already talked about this, but dissociation means basically ions are kind of broken away from one another. And I don't know if that's the best way to word it, but here's the picture. An ionic bond, again, is when we have two atoms that have a different charge, one a positive, one a negative, and then because of those differences in the charge, they're attracted to one another. An example here is our infamous sodium chloride. So sodium, positively charged, chlorine, negatively charged, these form an ionic bond because sodium gives one of its electrons to chlorine. Well, so these generally want to stay really close together, but once you put them in a beaker of water, these molecules right here, these are water molecules, they actually start pulling these things away. And you can see all of the negative charges on the oxygen are attracted to this positive charge on the sodium, and all of the slightly positive charges on the hydrogens are attracted to these negative charges. And so whereas you once had these two things bound together, the two ions, now suddenly they're being taken away because of water. When an ionic compound disassociates into its individual ions, we call that, no, I already said it, dissociation. Okay, so that's what it means. It basically means an ionic substance, the ionic bonds are kind of dissolved by water so that the two ions, rather than attached to one another, they can kind of float freely in solution. And so this is what's responsible for dissolving things like salt and sugar in water, is that very property. A couple other words here we need to talk about: adhesion and cohesion. And these things are pretty self-explanatory here, or they're pretty simple. Cohesion means that the tendency for water molecules are attracted to one another. Okay, so one water molecule is attracted to another water molecule. And in adhesion, rather than the water molecules attaching to themselves, the water molecules are attracted to other types of molecules. So cohesion, we're just talking about water and water only. Adhesion, we're talking about water attaching to something other than water. And these result in some important properties. For example, here we're seeing this is a water strider bug that can actually walk on water. Here we're seeing a pin which is made out of metal. Now this metal is much more dense than water. You know, if you put a big metal something in a lake or a bathtub, it sinks right to the bottom, doesn't it? So you have to ask yourself, why on earth is something that's much more dense, something like metal, floating on the top of this water? And the answer is that in this example is because of cohesion. You know, you've got all of these water molecules in this water, and they are all attracted to one another. And so in order for this thing to fall down to the bottom of the glass, it has to break through the attraction that the water molecules have with one another. And it's of a shape and a size that it's not big enough, not substantial enough to break that those attractions that the water molecules have to one another. This is called surface tension. And it's important in a couple of different areas. One is, for example, these guys, the water striders, are able to walk on water because that water will not break with such a light mass. And this thing here is actually more dense than the water, but it still floats because it's able to spread its weight out and not break the surface tension that's caused by the attraction of the water molecules to themselves. All right, so surface tension, it's also important like in the lungs, like your air sacs in your lungs have a lining of fluid that surrounds them, and the reason that that fluid doesn't beat up and form little droplets is because of something that actually decreases the surface tension so that they can spread out a little bit more. All right, so there's a kind of an anti-surface tension example. Okay. In either case, that's adhesion and cohesion. An example of adhesion, I guess we didn't really talk about it yet, is when you have this, which is called capillary attraction. So what this picture is trying to show you is if you put a glass straw, which is known as a capillary tube, into water, the water actually is going to overcome and defy gravity and climb up the tube above and beyond the normal level of water here. And the reason it does this is because water molecules are attracted to the glass sides of the straw. So you can see here right on the edge, the water is actually kind of climbing up. And so the water molecules will climb up, climb up, climb up, and then eventually it gets to a point where the force of gravity overcomes the strength with which the water molecules are attracted to the glass. But this would be a good example of adhesion. Alright, so that's a little bit about water. Moving on to pH. pH refers to basically the concentration of hydrogen ions. Okay, when I put these little brackets here that I've put, this forever from this point on you can know that that stands for the concentration. So how basically the abundance of a certain something per given volume. Okay, that's what concentration means. How much of something is in a certain volume or a certain container. Well, in either case, you know, we're talking about protons here, hydrogen ions. Remember, hydrogen has 1 proton and 1 electron and 0 neutrons. So if you have a positively charged hydrogen ion, it means it's lost its 1 electron. So now all it is just a single proton. So sometimes these are referred to as protons rather than hydrogen ions, and that's probably how I'll refer them to, or I'll refer to them. All right, so in either case, when you increase the amount of hydrogen ions in a substance, this will lead to a decrease in the pH. And when you decrease the amount of hydrogen ions, this is going to lead to an increase in pH. And a decrease in pH is to say something is more acidic, and to increase the pH is to say that something is more basic. And this is something that you should star and work through, because I guarantee you there's probably going to be a question on the exam like it, and many people will be tempted to get this one wrong. Okay, so because it's a kind of a weird relationship where you would increase something and then decrease it, or decrease something and then increase it. All right, so keep that in mind. Let's unpack this a little bit now after I've kind of laid that on you. So the pH scale is something that tells you how acidic or basic something is, and it looks something like this. It's a scale that runs from 0 to 14. Stuff that's 14 is very, very, very strong base, so it's basic. Stuff that is 0 is more acidic. So as we go this direction in the number scale, something is getting less acidic and more basic. As we go this direction in the scale, something is getting less basic and more acidic. The qualities of these things: basic stuff is usually like bitter to the taste, and certainly not all of these things you would probably want to drink, but it's really bitter. So if you eat something that's bitter, it's likely it's basic. Also, bitter stuff basic stuff is usually slippery for whatever reason. And like if you get some bleach water on your hands, you might notice that your hands are just kind of slippery. Whereas stuff that's acidic, for taste-wise, it's stuff that's really sour. Okay, so things that are acidic would be like, you know, right here, this is neutral, distilled water, so this isn't really acidic or basic. And urine is a little bit acidic. Coffee is even more acidic. Tomato juice is more. Orange juice is more. And then lemon juice, that stuff's real sour. That's got a pH of about 2. And then probably some of the strongest acid around is this stuff called hydrochloric acid, which is what your stomach makes. And that's going to be the thing that helps you digest your protein. So that's kind of on the pH scale for acid. Going on the flip side, things like seawater are a little bit basic. Baking soda is a little bit more. Ammonia is really basic, and then bleach water is really probably the standard of what is basic there. Okay. Now again, the thing that determines what pH something has is the concentration of protons. How many protons are there? So if you have something with a lot of protons in it, that means it's a strong acid. If you have something that does not have a lot of protons in it, a lot of hydrogen ions in it, then it is something that's more like a base. Okay, and then so if you kind of were to draw an arrow, this would be increasing abundance of hydrogen ions, and this direction would be you're actually decreasing the abundance of hydrogen ions. And this can be a little bit of a misleading definition when you get into real advanced chemistry, but for our purposes we'll stick with it. It just has to do with how many protons are in a solution. That's why we call this pH. The H stands for the concentration of hydrogen ions. Okay. All right. Now, what a buffer is it's something that keeps the pH stable. Okay. A real good example is in your body, you've got this stuff called carbonic acid. And even though it's called acid, it really is what's called a buffer. It helps to stabilize the pH. That's what a buffer does. And this is good because, you know, let's say you want to drink some coffee in the morning. Coffee is a little bit acidic. And if you didn't have a way to buffer the pH in your body, you'd drink some coffee and then your whole body would start to get a little bit more acidic. Or let's say you accidentally swallow some soap or something. I don't know, you swallow some soap and that would make your body a little bit more basic. And your cells need a very optimal range of pH in order to function. You know, there's a lot of components inside your cells that require a very narrow range. If anything gets too acidic or too basic, they just kind of shut down. So you have to keep a very stable pH in your body. And sometimes that can be tricky, you know, if you like to drink a lot of lemon juice or you like to, you know, do a bunch of other types of stuff that can change the pH. So your body has to have some way to keep it stable throughout all of those environmental changes. And that's where buffers come in place. And the main buffer system in the body is this one that's shown in the picture, using this stuff called carbonic acid. And what can happen is, let's say you don't have enough acidity in your blood, so your blood is becoming more basic and your body detects that. Well, this stuff here, it can actually dissociate into this stuff, which releases more of these, and this is going to go to then raise the acidity. Another thing that could happen is, let's say you have a bunch of this stuff in your body. This is called bicarbonate ion. This is literally the stuff that's in Tums or any sort of you know, stomach pill, or the substance that antacid is the word I'm looking for, the thing that makes your heartburn go away. It's also the same stuff as baking soda. Well, what can happen is, if there's a lot of this laying around and your body is too acidic, well then this can actually form this and then go this direction in the equation, and ultimately resulting in the release of CO2. Okay, so if you can either go this way to kind of get less acidic, or go this way to get more acidic, depending on the needs of the body. So this substance here, bicarbonate, or this carbonic acid, it sits kind of right in the middle, and if we need to increase the acidity, it will kind of drive the equation this way. If we need to decrease acidity, it will drive the equation this way. So it's a kind of an interesting way that the body uses to maintain a stable pH. All right, so here's here's a question that is geared to give you a little time to think about this. Go ahead and pause the video and maybe work out some of these things. And if you can't work them out, then you might need to go back and rewatch some of this stuff about pH. Okay, moving on. We're going to talk a little bit about carbon. Carbon is basically, when you hear carbon, think about the building block of big molecules. It's probably a better word of writing it is it's the backbone of molecules. So in the same way that you and I have a backbone, our skeletal system, you know, that keeps all of our parts anchored onto our backbone. You know, your arms and your legs are all anchored to your backbone. Well, carbon is kind of the same structure molecularly. And the reason why is because carbon atoms can form up to 4 bonds. And so when you are able to grab onto a bunch of other atoms, it makes a nice kind of support atom to connect stuff together. The reason why it can form up to 4 bonds, you might be able to spot why, is the fact that it has 4 valence electrons. And remember, in this shell, you want to have 8 electrons, or the atom wants to have 8 electrons. And so here I only have 4 of 8 in carbon, so it's going to want to try and get 4 more of these. And so what it can do is it can form 4 covalent bonds with an atom such as, with an element such as hydrogen, because hydrogen is willing to share its electrons. So if you add 4 hydrogens onto carbon, then suddenly, you know, you've got 4 hydrogens sharing their 1 electron with carbon, and then that equals a total of 8 electrons. So that's why it can form 4 bonds, because it's looking to pick up 4 electrons. And this is a big component in macromolecules. Macromolecules is just a regular old molecule. Again, a molecule is any time you have 2 or more atoms bound to one another. We call that a molecule. And when you have a macromolecule, that means a molecule that's really big. And there's 4 different classes of these macromolecules in your body. We're going to talk more about these in chapter 3. But for starters here, here's the 4. You have proteins, fats, carbohydrates, and nucleic acids. And carbon is kind of an important backbone atom in all of these big molecules. Carbon can also form these things called hydrocarbons. And that's basically when you have a bunch of carbons that are just attached to nothing but hydrogen. And these actually occur quite a bit in nature. So for whatever reason, carbon likes to just form these chains, and then it's almost like it doesn't really know what else to bind to. So it's like, I'll just pick up some hydrogens, might as well. So it just grabs a whole bunch of hydrogens. And these are pretty important substances. For example, you'll look at some of these, like methane. Methane is a gas. It's like pretty similar to natural gas, the stuff that you pump through your stove or your cooktop to cook dinner. Ethane is going to be another type of gas. You got propane, which is another type of gas. These are all like fuels that we use to make energy. Same with butane. This is the stuff that's usually found in like cigarette lighters. Pentane. And like gasoline is going to be a big, huge hydrocarbon. So they're really high energy molecules, and the reason being is because they're totally chock full of atoms. You know, they're really big, bulky kind of molecules. You can see they start to get these really big molecules, and all of the binding sites of carbon are just totally exhausted. So it's got a lot of atoms on it, and the more bonds a molecule has, the likely the more energy it's storing. So that's what a hydrocarbon is. You certainly don't need to memorize all of these hydrocarbons, but it is important to understand that what type of molecule a hydrocarbon is, because we'll talk a little bit more about those. The last thing we're going to talk about, and this is a pretty important thing to grasp as we proceed, are what are known as functional groups. A functional group is just basically a component attached to a molecule that gives it a special property. All right, so you can just have any old molecule, let's say. This could be a hydrocarbon, it could be some sort of sugar or protein, any molecule, you name it, whatever. Well, if that molecule has a certain thing attached to it, it's called a functional group. And it could have all sorts of functional groups attached to it, but it's the functional groups that usually determine what kind of characteristics it has. So to understand, you know, if you can look at a molecule and understand perhaps how it might behave, the way to do that is by knowing what kind of functional groups are on that molecule and how they behave. Because if you know how the functional groups behave, then if you see them on a molecule, you might have a suspicion about how it behaves. So there's about 6 or 7 of them, and we'll just briefly talk through them here. The first functional group that you might encounter on a molecule is what's known as a hydroxyl group. And that's when you just basically have an O and an H attached to the molecule. This little thing here, R, that's just referring to something. Okay, so R is just referring to the rest of the molecule that is not pictured. Okay, so O and H together, these things, OH is one atom of oxygen bound to one atom of hydrogen. Usually, if it dissociates into an ion component, it's called a hydroxyl ion or hydroxide ion. Okay, but in either case, what you might speculate here about this type of group is, remember the interaction that happens between oxygen and hydrogen. Oxygen has a high electronegativity, which means it likes to hog electrons. And in the bond between oxygen and hydrogen, which, by the way, these little sticks here that you see, I don't know if I've mentioned this before, those sticks tell you that there's a bond, a covalent bond there. So this is a covalent bond. Electrons are being shared between these things. In either case, though, oxygen is highly electronegative, so it wants to pull the electrons there, so you know that there's going to be a slightly negative charge on the oxygen, a slightly positive charge on the hydrogen. So knowing that, what can you tell me about this type of functional group? Well, I'm hoping that you can, at least at this point, figure out that it's polar, right? Because, again, we've got our electrical poles. And generally, if you find a molecule that's got a lot of oxygens in it, it's probably going to be polar, just because, again, oxygen doesn't share very fairly its electrons. There's another type of group that's basically just some sort of molecular part, and then onto it is bound a carbon, and then 3 hydrogens like this. This is called a methyl group. Remember this component, like we just talked about on the previous slide, this is methane. One of the simplest kind of organic molecules out there. Well, when you have that C with 3 H's, it's called methyl. And what could you tell me about this group? You got a carbon. Carbon generally shares its electrons fairly with its partners, right? So that means that the electrons spend the same amount of time here as they do here, so that means there's probably not any poles, because there's no slight charges on this molecule. So this would be a non-polar group. The next one on the list is the carbonyl group. This is when you have part of a molecule and another part of a molecule. Again, the R just refers to some piece of a molecule. We're not told exactly what. And then in between those two chunks of the molecule, there's a stanza carbon, which has 2 bonds to oxygen. Okay, here's one bond, here's the other. Again, each one of these sticks refers to a sharing of electrons between atoms. So this means that not one electron is shared between them, but 2 electrons are being passed back and forth. Okay, so this one, we see that we have an oxygen. So we're probably suspicious that there's a little bit of polarity going on here. So oxygen is going to pull the electrons towards itself, and that's going to put a slightly negative charge here and a slightly positive charge here, and that is in fact the case. This is a polar group. It's not probably as polar as this, since oxygen can't really hog as many electrons from carbon as it can from hydrogen, but it would still probably be polar nonetheless. Okay, here's an interesting one. This is called the carboxyl group. Don't get that confused with the carbonyl group. They look almost identically, don't they? Here we both have a chunk of a molecule which then is bound to a C, and then there's a double bond to oxygen. But here's the big difference between these groups. In the carbonyl group, we just go back to the rest of the molecule. But in the carboxyl group, we're ending. This is going to be kind of a terminal group on the end of a molecule. And so, rather than continuing on, it actually ends with another hydroxyl group. Okay, you may recognize this OH here. That's what we're seeing. So let the name give it away, because this is hydroxyl. Keep in mind drox, and you see that same word in carbox. Okay, so when you see this box, let it remind you of the hydroxyl group. So then you know that this is a carboxyl group, not a carbonyl group. Okay. Now let's think about what this functional group might do. It looks like this, and we know there's an oxygen here, so it's probably going to be polar. There's another oxygen here, so it's probably going to be even more polar. And then for whatever reason, I'm not exactly sure why. You could take an organic chemistry class if you wanted to figure out why, but for whatever reason, this hydrogen ion sometimes can leave on this group. All of these bonds are stable enough where this can just kind of head out. And when it heads out, it leaves its electrons behind. So then it actually ends up being just the proton, and then oxygen will hold on to those electrons, creating two separate new things now, a proton plus this group. So because of that tendency for these types of groups to dissociate in that manner, this is called an acid, right? Because we said anytime you're increasing the amount of hydrogen ions, you are decreasing the pH, and that is the same thing as increasing how acidic something is, the acidity. Okay, so carboxyls can sometimes be acidic groups for the very reason that they can sometimes release these hydrogen ions into a solution, which is going to increase how many hydrogen ions there are. Okay, moving on, we have the amino groups. Amino groups are kind of interesting. There's going to be a little bit of polarity probably here, just because nitrogen is pretty close to oxygen in the periodic table. So it's a little bit electronegative, and it's maybe going to pull in some of the electrons a little bit, so there might be a slight positive charge here, a slight negative charge here, a slight positive charge here. But what's interesting about these groups, for whatever reason, hydrogen ions, protons, are interested in attaching to nitrogen. The reason is because nitrogen has two free electrons here that aren't bound to anything, and a lonely little proton is looking to fill that outer shell. So that's kind of the organic chemistry behind it, but that's a little bit beyond what you need to know. But you should know that hydrogen ions like to attach to nitrogen. And because of that, this will form this group here, where it's R, N, and then it's actually bound to 3 hydrogens, and now there's actually a positive, overall positive charge on here because you've just added a proton without adding any electrons, so that sways the balance of the electrical charges here. Because remember, you see in this group there is no charge presently, so that means that can tell you that this whole molecule is electrically balanced. The same number of electrons is the same number of protons. Well, if you just add a charged proton here without bringing on any more electrons, then that's going to give you a net charge of a positive on the molecule. Okay, so this is my question to you then. Because this molecule will kind of soak up or take out protons from a solution, do you suppose that a group like this, is this an acid or is this a base? Take a minute just to maybe pause the video and see if you can think about what it would be based upon what you know about acid-base chemistry. The answer is going to be that it's a base, because what it's doing is it's removing these protons from solution. And anytime you decrease the number of protons that are in a solution, you will increase the pH. That is to say, to decrease the acidity and increase how basic something is. Okay, things with a higher pH are more basic, less acidic. So, what's interesting though is that this amino group, the one that's right here, this is basic. But then after it soaks up that hydrogen and it forms this thing, this is actually called an amino acid group. And that's because at any point in time, this thing can actually leave again. So it can attach on or it can leave. And so before it attaches, then the group's called a base, but then after it attaches, now it's called an acid because it can release hydrogens back into the solution. So a little bit of an interesting group there. So these are considered basic in this form, but after they pick up the hydrogen, then they suddenly are switched, and now they're acidic. All right, 2 more to go. Phosphate group. This is the only one with phosphorus on it, so let that help you. And you can probably tell me here, what do you think? Is this group polar or is this non-polar? Here's the group, and you can see we've got oxygens all over the place, right? There's 1, 2, 3, 4, and if you know anything about oxygen, it doesn't share its electrons all that fair. So there's going to be slight charges all over the place on this molecule. This is going to be slightly negative here, this is going to be slightly negative here, this is going to be slightly negative here, this is going to be slightly positive on the hydrogen. So this is a very polar group, okay? And also, because there's so many oxygens attached to the phosphorus, what can happen is that I drew this incorrectly. Let me fix this quick. There's a double bond to oxygen and then 2 hydroxyls. What can happen is that this hydrogen can peace out, this hydrogen can peace out, head out, and this particular functional group, the phosphate group, can actually release 2 protons, and then that leaves a pretty substantial negative charge on the molecule, the group. So this is a pretty strong acidic group because it can release so many hydrogen ions. So these are also considered acidic. Okay. And then lastly, we have the sulfhydryl group. This one is pretty similar to the hydroxyl group. Okay, we have sulfur instead of oxygen. Sulfur is a little bit electronegative, not nearly as much as oxygen, but it's still going to pull some of those electrons towards itself to create some poles. So this is actually a polar group as well. So here's what I want you to do. Take a minute, and I'm going to breeze through these. See if you can guess the name of each of the groups, and then if you can give me a brief description of its characteristics. If you can do those 2 things without looking at your notes, you know you're doing pretty well for functional groups. So here's a word bank. Here's the first example. Which one is this one? What about this one? Do you know what this one is? And again, for each of these, can you maybe pause it and tell me a little bit about the molecule? All right, so that was the list. We'll go through it and see if you got them all right. Okay, this one right here, the first one, you've got a C attached to 3 hydrogens. Okay, so this is a methyl group. The next one here, this is it's got a double bond to oxygen, and it's got a hydroxyl group on it. So this one is the carboxyl one. And remember that this one, it's going to be polar because we've got oxygens on there, so there's going to be a slight negative charge, a slight positive charge. And then this one, for whatever reason, can head out and increase the amount of hydrogen ions in a solution. So this one is going to be slightly acidic as well. Oh, I forgot to mention something about the methyl group. This one is non-polar, right, because carbon shares equally with all of these things, so there's no charges. Okay, moving on to the third one on our exercise. This has got phosphorus in it, so that's the phosphate group. And this one is going to be polar. Again, you know that because look at all the oxygens, okay, and they're all creating charge differences. And then this one's also going to be acidic because this can decide to leave and this can decide to leave. So each one of these could release up to 2 hydrogen ions into solution. This is our infamous hydroxyl group. There's not much to say about this other than oxygen's hogging electrons from the hydrogen, so this would in fact be polar, because we're going to have a slightly positive pole here, a slightly negative pole here. This is the amino group, and this one's a little bit interesting because there's 2 electrons sitting around. That hydrogen protons, or that protons are tempted to attach to. So it's going to go flunk. And when that happens, because this was electrically neutral to start with, and then you're adding a proton on it without adding its corresponding electron, you end up getting a 3 hydrogens attached to it, and then a slight positive charge, or actual positive charge, a positive charge of 1 on the molecule. And then, so this thing is an amino group. It can soak up hydrogen ions, so it is basic. But then the result is a group that's called an amino acid group. And as the name suggests, that is, guess I'm running low on battery. That is an acid group. Here we have a carbon, double bond to oxygen, but there's no hydroxyl group, so this must be the carbonyl group. And it's a little bit polar. It's not much to say about this one other than there's a slightly negative charge here and a slightly positive charge there. This is the sulf hydryl group. Sulf stands for sulfur, hydryl stands for hydrogen, and we have a sulfur and a hydrogen. Sulfur is kind of like oxygen, so it does hog some of the electrons from hydrogen, so this is a polar group. So on each of these, could you tell me polar or nonpolar, and then which ones are the acids, which is a base? And then, based upon whether it's polar or nonpolar, could you tell me if it's hydrophilic or hydrophobic? If you can do all of those things, you have got a really great grasp on this chapter. Let me know if you have any questions.